Welcome, everybody. I'm Paul Goosens from MapleSoft. So I'm basically the master of ceremonies for this session. Most of the heavy lifting will be done by Malco and Mohammed, two pretty seasoned consultants that we've been working with, particularly in the area of product line engineering. Malco, as well as being part of his own company, MBSE Consulting, is also working currently at Airbus on a PLE project. I'm also joined with Brani Mohan, who is our MapleMBSE product manager. We'll be around mainly to field any questions about the platform at the end of this session. We're expecting the whole presentation to be around about 45 minutes, which should give us plenty of time for questions and discussion. Before we get into the presentation itself, I just wanted to give you a little bit of an introduction to why we developed MapleMBSE. What was the motivation behind this, and largely just out of our activities on the engineering design side of things and the analysis and simulation side of the engineering design process, we were observing a lot of interactions between traditional customers, the design engineers, and the systems engineers. And typically, this would be around the systems model, which would be considered either the single source of truth, or the authoritative source of truth, which defines what the goals are of the system design and operation. So the systems engineers would be the ones creating the systems model. And then many different stakeholders, not just design engineers, but safety engineers, business process managers, all are involved in the project, and they need information from the systems model in order to do the work that they're doing. And once they got that that work, the results of that work has to be then transmitted back to the systems engineer, typically in a fairly ad hoc way. It'll be emails, documents, spreadsheets, and so forth. And then it's down to the systems engineer to decode all that information, to populate the information back into the systems model. And this is where we're seeing a fair bit of friction. It's a very human process. So there's a lot of misinterpretations or miscommunications. Errors start to creep in, and this ends up with a lot of time wasting rework or investigations, endless design reviews trying to address those problems. And then this just sort of erodes not only the efficiency or the efficacy of the process, but also it erodes confidence in the process itself. So what we're proposing is why not give all the project stakeholders direct access to the systems model. They can take the information that they need in terms of a view into the systems model, and then make any changes that they need to make, or add further information to the systems model directly into the model. But we can't expect them to use tools like Cameo or Rhapsody to do this. These are tools that are specific for systems engineers, and also have a much broader scope than simply just adding further information. So we thought, well, why not give them Excel? So we have created a tool that allows all the stakeholders to see those views that are specific to the work that they do, and then add the changes. And this could be in terms of more detailed subsystems at different hierarchies, or could be changing parameters. Everything can be done within the Excel environment. This now facilitates that whole process by basically providing all that information in a consistent and appropriately integrated level into the systems model, and that just makes the whole design review process a lot easier, And once any changes are discussed and agreed, then the engineer can simply authorize those changes into the main systems model. But this isn't just about facilitating the collaboration between the systems engineers and the stakeholders. It also allows various different stakeholders to collaborate with each other through the systems model. And this is actually one of the sort of tasks we're going to be seeing here in the context of product line engineering, so variability management, as part of those tasks that can be done in collaboration through the Excel user interface. So that's really our driving motivation for developing MapleMBSE. Just to be clear, MapleMBSE provides an intuitive Excel user interface that allows you to enter and modify system information in an appropriate way. But it also, at the back end, it provides a very tightly integrated bidirectional synchronization between the systems model and the front end in Excel. So this is not about file import and export. This is truly using Excel as a user interface to the systems model. It's highly customizable because you have many different tasks, and you'll see in this presentation one example of the tasks that MapleMBSE can be configured to perform. And we currently are integrated with pretty much the standard systems engineering platforms, specifically Rhapsody from IBM, Magic Draw, Cameo Systems Modeler through Teamwork Cloud. And then as of last week, we also support Capella. So in a nutshell, what MapleMBSE is doing is it's allowing or facilitating the ability to collaborate across the enterprise through the systems model by just making it easier to access and that information and to enter information. This reduces that friction between the systems engineering function and all other stakeholders, therefore reducing errors, costs, and all that good stuff. But more importantly, it really helps to increase the confidence in the process and then broadening engagement with all stakeholders through the systems model. So that's really setting the scene for this presentation. What we're going to see here is a specific example of the use of MapleMBSE in variability management. So I will now pass this over to Marco and Mohammed. And you're muted.
Yeah, thanks, Paul. If you can stop sharing, exactly, so now I can share my screen. Okay, very good. So, welcome everybody, and as Paul introduced, I'm going together with Mohammed today to introduce the MapleMBSE for variability management. So let's go quickly through the agenda. As you can see, we first start with system variability with a real example, trying to explain what is variability and why we need to manage system variability. Then we will briefly introduce the ISO standard 26550 that describes the PLE approach. That's one way of managing variability. And we'll go into the PLE approach. To then continue deepen the methodological aspect that we call SysPL. And then we go to the core of this presentation, that is a demo that is based on Excel-based MapleMBSE for variability management and Cameo System Modeler. And we will present you the use case in which this approach is beneficial. and finally the sum. So, first of all, what is system variability? Let's take now the example of a big aircraft manufacturer that is producing two different products. This could be, for as you can see here, a commercial aircraft or a military aircraft. In this case, the company aims at reusing as much as possible between the two different programs, even if there are huge differences. The key aspect here is to understand what can be reused and how it can be reused. And that's why enter here into the discussion the topic of which are the variability drivers that drives my variability. And if I identify these drivers, I know exactly what vary in my system and what remains stable, and I can manage properly my variability. And ultimately, I can reuse across the two programs. If we take the example of a subsystem that can be reused between the two type of products, that can be the propulsion, we can see that the variability is driven by several aspects. For example, the installation of the tanks, where the tanks are installed in the body of the airplane or in the wings, the type of tanks that are used, the amount of tanks that are used, but also the refueling method that is used to refuel the airplanes and the type of system that implements that. The type of engine, you can imagine that it's really different if you are going to perform a mission, if you have a military operation scope or a commercial scope, the engine will be different. Also, the performances of the engine will vary. And the propulsion technology used can also drive variability and many other aspects. One exemplary is the mileage range, but we can identify also other drivers of variability. So the key question here is how to manage this variability, this system variability, and what is common, what must remain common, and what can be variable. If we move to the next slide, now we have the question, and why is it important to manage variability? If we took an aerospace perspective, we can identify the three main motivations to manage variability. First is the complexity management aspect. As you can see, aircraft are really complex systems that have a lot of interdependencies. Now imagine if you change one, or if you add variability in one of these components here, that have so many interdependencies, which can be the impact of changes in your system. Huge. So it's important to understand what must remain common in order to avoid the increase of complexity and what can vary because it's not drastically impacting the complexity of the system. Second aspect is the reuse aspect. As I mentioned before, aircraft manufacturers, but also other engineering companies aim at reusing as much as possible. And variability management enables the reuse of components, functions, and other engineering artifacts across different projects or programs. And you will not only cut the non-recurring costs, but ultimately also the recurring cost, since you are taking advantages of economies of scales. Third aspect, last but not least, if you manage variability properly, then you speed up and improve your system development, so you have a faster time to market, and at the same time, you decrease the time needed to achieve a certification to authorize the operation of the airplane in this specific case. So as you can see, these are just some of the key important motivations to manage variability. But we can identify much more than that. One way to manage variability is through the implementation of product line engineering. Product line engineering, as described by the 26550 ISO standard, it's a discipline, it's a mechanism that enable the creation of a product line, also called platform, in the so-called domain engineering phase, what is on top of this picture. And from that, many products can be derived, also known as single product or applications. And this is what is covered in the application engineering part. We base our work on this standard because it's our lighthouse in the topic, in the area of product line engineering and variability management. According to the standards, we can simplify the understanding of variability management by using this visualization. That is the so-called four quadrants. You can see that we have on the bottom, on the upper part, the domain engineering from left to right, and of the bottom, the application engineering. So the domain engineering is where the variability is defined, created, and managed. And the application engineering is where the features and variability are configured in order to generate several applications or several single products derived by the platform. So domain engineering is always associated with the platform. That's the part where the variability is defined. Application engineering are the single products derived by the platform. Now, the focus of this presentation and of this demo is the left side. So we are going to cover domain and application engineering, but what concerns the feature and the configuration of the features. For example, if you take this small example here, if the configuration 1 have, as you can see here, as a commercial operation and a long range operation. So I select these two features, and these two features and the information regarding their variability are defined on this level. In the bottom are basically configured. So now I'm going to hand over to Mohammed, that is going to go deeper and explain better the methodological aspect.
Thank you, Marco. I will share my screen. Okay. So thanks again. After we have now introduced the variability management topic, let's dive now in details of the methodological aspects. And it's pretty much about identifying the main concepts for a proper model-based system engineering solution. So in order to deploy any model-based system engineering application for any domain, we have to define a set of key building blocks or set of components, what we see on the picture in this slide. And actually what we see here is adopted from the best well-known article from Stefan about the evaluation of different methodologies, and mainly highlight the definition. What does methodology means? And clearly state that methodology is a set of processes, methods, tools, for sure the environment. We extend it here with the ontology, with the modeling language, because we find it as a very crucial part. So it's most important that you take here, there's a big picture, and in the following slides, we will dive in each one of these components. So with respect to the first part, I'm very sure everybody have heard about process and everybody knows what does it mean. But unfortunately, typical processes are normally historically being extended with a lot of information, with a lot of methods information, or maybe with tools, and getting so advanced that they are not really usable. From a SysPL, Systems Product Line perspective, here we highlight the ISO 26550, as Marco mentioned before. as the best standard at the moment for the software and systems engineering, and really provide a very good start for those who are starting to discover the PLE, to have a common terminology, to have a proper definition, really for building the process. However, for advanced users who are already applying product line engineering, they might find that this kind of standard lacks additional information which make them really implement exactly what they need. That's why the process, I would just highlight that there is still a lot to do on the community behind, and if I see the last years, it's getting better and better. With respect to the environment, it's very important not to forget about it. It's here generalizes all organizational aspects, resources, financial, other human factors, etc. It's outside part of the presentation. I'll refer you, if you Google, you'll find the article and you'll find more information about that. If we move to the second part, which is the methods, and here it's mainly about defining the how. Is exactly how you do it. If you meet your colleague, or if you meet a competitor and you think, oh, you need to know how he did it, and it's really the secret. And normally the methods is really the part which costs a lot, not only money, but costs a lot of time to find out how to do it best, how to do it the best way to exactly achieve with respect to MBSE. The method part is as well is a very hard part, because it's very linked to the process. We need to look at what we do and then see how to do it from one side, and from the other side, it's very much related to the tool we use. It's also very much related to the ontology or to the modeling language we use. For this scope, we focus on the feature modeling method, and as you see, it's a task, a collection of other tasks. And if we're going to open the box and see what's the subtask of that, it's going to start with the feature definition is the time when we start to define features. Here we don't say if it's in Excel or if it's in Cameo. We just say exactly, we're going to show later in the demo how we can do it. We define the feature model elements, which just collect a set of features. Then we define the feature of the system under system of interest, and mainly we define the feature relationships, which can be in the second slide, all the dependencies between the features. After the feature definition, the second step is related to the feature analysis, is where we really come and take the system engineering hat and apply the holistic thinking and check the whole features about maybe all the subsystems, and maybe the features also from the supplier or the features from the customer wanted, and analyze all the dependencies and definitely verify and validate very early in the modeling phase, not very later when we are implementing the solution. These are followed by the feature configuration, is exactly what the picture showed from Mark when we jump from the domain engineering to application engineering, where we define a set of configurations, we select the previously defined feature to these configurations, we visualize the configuration, and we see, does it really make sense, for example, to have a 10 different set of configuration, or can we minimize it to 5, because in that we are having more standard projects and products on the market. It's very important to highlight it's not a straightforward. We don't have to do task 1, then 2, then 3. It's a really iterative process, and that's what we're going to definitely highlight in the demo you will see next. On the third part related to the ontology, there's a lot of approaches have been developed about describing the modeling language, and it's really about enhancing the method and the process, so the what and the how, with a common terminology to ensure an interoperability between the human language, we as a human, the language we have in our brain or the language we talk, and the machine language, which actually the model, the language we're going to represent in the model itself. Indeed, we are aiming also at more semantics, or other words, the same, that we have the same meaning and avoid ambiguity. I'm sure most of you have heard about SysML as a common standard, as that common standard language for among systems engineers. Unfortunately, there is no one accepted standard yet for variability management available on the market, and historically, a lot of approaches have been driven to use SysML on that. We do that. So we use on the latest version of SysML 1.5, or now the latest. But we also know that SysML 2.0 is expected to provide a better solution. So everything which can be developed on the SysPL will be for sure migrated if SysML 2.0 when SysML 2.0 is ready. What we see here in the ontology is very simple, actually. That's it. This is our feature modeling ontology. The most important element is the feature, is exactly what's going to be solved or what the customer want to see, the very high abstraction. There is some logical dependencies, mandatory and optional. Mandatory is really a feature which can be definitely across all products. Optional is it's going to be a feature going to be only for particular products or particular customers or particular maybe continental. On the other side, there are dependencies between the feature. We could pick up feature A or feature B, or we can pick up feature A XOR B. So either we have to pick up A or B. Nevertheless, it's very important. On the right side, you see there are constraints that if we pick up feature A, we cannot pick up feature B, or this is what excludes and requires is very, as it says, if we pick up feature A, we have to pick up feature B. So that's actually what's related to feature modeling, which is done during the domain engineering. When we step to the application engineering, we need to define additional elements, which is a feature configuration, and we just make a link to exactly say which feature configuration is selecting which set of features. The feature model is here as a container. I'm gonna just keep it now at this level for this slide. And after the ontology, actually, we come to the one of the most important parts. We're not going to stay on paper. We need to follow the state of the art. We need to find the right tool, and actually it's in reality it's not that tool, it's a set of tools. It's about the ecosystem of the whole tools. What we show here in our solution that as Paul mentioned during the introduction of MapleMBSE, we are not only considering MBSEers, which are on this side down, but we are definitely interested as well with non-MBSEers, or those who really doesn't know MBSE, and we know it's very difficult to put them on the table of MBSE. But it's not only about the human roles, it's about also the data they are exchanging. It needs to be consistent, it needs to be unique. We need to have it from a single source. We need to also manage read-write access, and etc. So what we see now in the actual solution, what we see now in the actual solution is actually we expect a systems engineer, so an MBSE working with a SysML modeling tool. As Paul mentioned, it's not necessarily Cameo, it could be other SysML modeling tool. That tool here is Cameo, provided with the Teamwork Cloud, or where all the data are saved with the suitable configuration and version management. On the other side, we have not only two, we could have as many as possible Excel users. Each one has his own sheet with his own user interface, with his own selection viewpoint, what information would like to see. And the main key here is the MapleMBSE part, which is actually, excuse me, the MapleMBSE part, which is really bridging the gap between these two worlds, which we're going to see now as next in the demo. So with that, I would hand over to Marco, and it's enough of talking. I think it's time to show a bit of action. I'll stop the sharing.
Thank you, Muhammad. So I'm now will introduce you the first user story of the demo. So we are first I will quickly introduce you the example, the propulsion example that we used for the demo, and we will use this example to run two user stories. So in the first user story, what you will see is that there will be two system experts, so they don't know anything about the MBSE approach. They don't know have any model-based knowledge, and they are going to define the variability through the features on the spreadsheet, on Excel in this case. And after they have defined the variability, they will save the information, and without having any interface with the tool, they will do everything in Excel. Then the MBSE, the system engineer, so the knowledge guy about MBSE, will see what they've done. Will they analyze the variability they have defined with the support of the tool, and eventually will update the features if needed, and then it will save, and so that the expert can open again the spreadsheet and validate and review eventual changes performed by the MBSE. So I'm going now to jump into Cameo system model quickly. That's the tool we used. So the example is, as I said, an aircraft propulsion example. So the propulsion subsystem for this example includes the fuel storage and distribution subsystem components, but it doesn't include the engine, because we are going to take the perspective of the aircraft manufacturer and not of the suppliers. Usually the engines are delivered by the suppliers. So when we define the variability for the propulsion, that it's distributed this way, as you can see in the airplane, we are usually, we don't just look at the subsystem propulsion variability, but we need to get input from above, from the aircraft, because the variability at aircraft level is different than the variability at propulsion level. And also we need to get the inputs variability from the components that are usually delivered by the suppliers. So we are going now, for a matter of simplicity, now we have identified two, as you can see, two feature models for this context. So it means that the propulsion, if I want to develop a propulsion subsystem with variability, I will have the features that are under my scope, the scope of the propulsion team, that are defined by the propulsion team. But also I need to consider features that are defined by other teams. In this case, for example, the aircraft team. And that's why the propulsion team is defining his own feature, but also using features from other teams. By having this approach and this organization, we also can enable collaborations between the different teams when they define the feature models. So now, after I introduce you this content, I'm going to show you that some features have been already defined in Excel in the tool. And we have here, for example, the so-called variability tree or feature tree. As you can see, we have several features that have been defined for the aircraft level. The aircraft range, the maximum pure capacity, and so on. And then we have also other features that are being defined for the propulsion. As you can see, the variability tree here is much more complex, and we have much more features. And these are the features that are being already defined. So now I take the hat of a person that doesn't know anything about MBSE, but has a full knowledge and deep knowledge of the system, in this case, the propulsion system, the aircraft system. And I'm going to I'm going here to go to my system feature hierarchy tab in Excel. So, and I'm going to add additional features to the features that have been already defined. As you see, these are exactly the features that you saw in Cameo. Now I'm going to define additional features. And what I'm going to define as features, it's called air-to-air refueling. I'm adding these new features. Air-to-air refueling is basically a feature that enables the refueling of the fuel of the aircraft on flight. So without any turnaround, without that the airplane or the aircraft stops. And now I'm going to add here these features. This feature also can be performed in different ways. So we have usually two ways. One is called the flying boom. That's the new technology. It's a faster way of refueling the airplane with another airplane on air. And then we have the older approach called probe and drogue for the refueling of the airplane. And this approach actually it's more used when there is an existing product where there needs to be integrated ahead after this adapted these features, no, the air-to-air refueling. So now here I define this step, the hierarchy, so the feature that I need, plus the hierarchy. I quickly update my model. So we have my feature now here. And then I can see now in my system features that also my feature have been updated. I can eventually here add some information about the feature. So I would say here that the air-to-air refueling is, let's say, enables the refueling of the aircraft on air. And I can add here some documentation to my features. So after I define the features, the hierarchy of my features, I can go now to define the variability information of my features. So I go to system feature variability, and here I have I will add now one information, and I would say that the new feature, the air-to-air refueling, is optional for the aircraft. As you can see, not all the aircraft have these features, but just some of them, especially the military aircraft. Okay, and that's why I'm going to add here these features. This is optional. Air-to-air refueling is optional for the aircraft system feature model. Now, we should also add here the information about the XOR, about the two features that are the air-to-air refueling as the XOR, the flying boom, and the probe and drogue. But in this case, I'm not going to add this information because I want to, I will fake that I forget as a system expert to add this information. So I will continue now with my example, and after I've defined my features, I will start to add additional information. As I said before, not all the airplanes have the air-to-air refueling, so I start to define some constraints. I know for sure that air-to-air refueling cannot be implemented in commercial operation, in commercial airplane. Why? For safety reasons, because you are carrying passengers, and is not allowed to have air-to-air refueling for commercial operation. That's why I'm going to here say that air-to-air refueling exclude commercial operation. You can see. Now, in this case, I also know that there is another constraints that is called required constraints. So before was the exclude, now is the required. And as if I now put the head of the propulsion expert, the propulsion expert can see, always it doesn't have any knowledge about MBSE, that a new feature, air-to-air refueling, had been added. And then he can say, okay, I know as an expert that if I have this feature, I need to, I require the body tanks at propulsion level. Why? Because to facilitate the collection and of the storage of the fuel. That's why I say here that body tanks are required from air-to-air refueling. So at the moment I added my information, I'm going to save. I added what I want to save. I'm going to commit. I'm saying new feature added. And then I'm now handing over to Mohammed.
Okay, thank you very much, Marco. You should see on the right bottom sorry, I thought I'm mute. You should see in the right bottom that I got notified. I am now the MBSE, or the systems engineer, and I got notified that on the database there's a new model, because Marco just saved his Excel file and committed a new version. So I'm now on my side, the version 98 is opened using Cameo. For those who know, you can update. I'm now asking the server, please show me the latest version. And it's going to take some time. We are in Europe and the other server maybe. And what we can, okay, what I can see, Marco, that it's the feature is not here. Did you save? Let me double check. Okay, I'm doing my system engineering job. I just got information that a new feature was added. Marco, did you add it under the?
Yes, it's added, as you can see.
Okay, I will check my Excel side, so just to be sure.
I will save again.
Okay, yeah. Okay, just try maybe to save and commit. Did you add a comment as well?
Yes, I do it again.
Mm-hmm.
So I edit.
Okay.
Then reload the project.
Yeah, I'm just gonna. Yeah, so now we see maybe it's just it's a commit, but I can see now that the air-to-air refueling is added. That's what I got information from Marco. And now I'm doing my system engineering job, is I'm doing really this holistic functional analysis step. So part of the things, first I'm gonna lock the element. I cannot now change anything. I'm interested to lock exactly for the system level. And I'm also interested to lock this diagram to do my analysis. So one of the things I will do, I'll just simply drag and drop this feature and do my analysis, ask this feature, please show me everything you're connected to. I can select now, okay, I don't want to see requires and exclude. I will see this in a different, I'm very interested in optional. I'm not gonna use this one. Excuse me, I'm gonna use just all the pass. So show me what's actually connected. As mentioned, I'm not interested in exclude in this view. I'm gonna do this later on, another view. Here I see two relations. One of them is the containment, which I know already. It's air-to-air refueling. It's hierarchically under the aircraft system. I don't want to see it on this diagram. I'm definitely interested in the optional part. So perfect. I can just quickly change the layout. And I assume it's here. Okay, now I'm gonna dive in the details, because as a system engineer, okay, it's air refueling. I see we have two options, two possible features. Let's see what's their model. So if I go to display related elements, I see the lack of XOR or OR. Again, it includes in range. I'm interested in the containment, the hierarchy. For that level, it's upper level. I'm not interested. Okay, I come back to the features now on the other side here, and I directly identify the mistake, which was faked by Marco, is that it's hierarchically correct, but we are lacking the XOR information, because as system engineer, I can go back to the requirements, to my requirements database, and I definitely know that we cannot put both. We have to pick one of these options. So definitely now I have also because as a system engineer, I have also the power to do so. I just directly add the XOR because I'm sure about it. And in this way, now I identified the missing part, and I can for sure also analyze it with another way with Cameo, using a very intuitive way. For some people, it's just better to use the relation map. This is, for example, now the whole aircraft. I'm not interested in the aircraft. I want to see more information only to air. And then here I can dive and see, oh, there is more information. So this is what I added now. You can see air-to-air refueling, and the relationship here in dark green are actually the XOR. It's not the container, it's only the logical, which we saw in the ontology. I can see that, okay, Marco added 2 additional requirements. I definitely can go to the properties window and also see more information for the traceability, where it's selected, all this stuff. But this we're going to see in the second use case. So for now, I did my job mainly by identifying the lag of XOR, and I would like now to commit that, save it to the server. So I'm generating now from 100 the new version of 101, and I'm going to say added XOR relationship. Fueling feature. And I will make a comment. I decided to leave everything free, so I don't lock anything else. And now I will hand over to Marco, where we expect to see this XOR missing added.
So yes, so now I'm going to open the Excel and see the changes. So let me share. You stop sharing, Mohammed?
Yes.
Okay. No. So now I'm going to live. I'm going to reload the projects.
So exactly. Yeah. If we see now what will happen in the has XOR row column, sorry.
We don't have, you see, you don't have any information here for the XOR. Now I'm going to reload. You tell me that something has changed. And now it's loading. So now I expect to see the, we should have under air-to-air refueling here. I should have.
Marco, we're not seeing the Excel file.
Okay.
Yeah, no. Okay.
It was a connection problem. Can you see now?
Yeah, we are seeing now.
So now you see we have under air-to-air refueling. Now the flying boom and probe and drove have been added. Okay. So the second use case, I don't know if we have time because we are running out of time. I'm going to quickly introduce it. And so before we just covered the variability aspect, the domain engineering aspect. Now we are going to cover, our idea was to define the feature configuration, always as non-MBSE. So in this case, it would be the sales expert, define the feature configuration. And in the spreadsheet, in Excel, then he will select the features that are needed according to customer requirements for the specific configuration. Then it will save. And then MBSE, as it did before, analyze and eventually update the selection for the configuration. So this is the second user story, that it's a similar approach, just the scope is changing, not the domain engineering, but in this case, application engineering is the configuration aspect. So I'm going to do it quickly. So now I go to the configuration aspect in my tabs. So here I have configuration. I'm going to add a new configuration. It's called configuration 4. And then I will have now this configuration here. And this configuration I know is a military product, and it's going to be really the same of configuration 1. So I'm going to copy here, let's say, the features that are needed. Plus, I'm going to add here the air-to-air refueling that is needed in this configuration. And I'm going to add the flight bung as a feature. So after I define the features, for my configuration, I commit again. Conf edit. And now I pass to Mohammed.
We can see just in the upper file of the Excel from Marco that it's also the same. He can see the number of the version. Okay, thanks, Marco. Then I will share my screen. And now, as you see, I get also notified that a new version of the server, and I expect, now we know it, but I expect the configuration 4 to show up here when I make the update. So configuration 4 is there. I know it's always still about the air-to-air refueling. What I'm interested now again to analyze is the systems engineering hat. I'm going to check all this, my to-do list, what to check everything. And now mainly I'm interested about more because of the configuration. It's not only XOR and logic like before, it's definitely excludes and requires. What I'm showing now, it could be also executed using Cameo validation rules, but it's out of the scope of this webinar today. So I go to air fueling very quickly, and I see that, okay, it requires the body tank. I know that the tank the body tank is another here, and I can see here, if I highlight this part, is not yet selected. So this is actually, there is an issue here, because if we selected the air-to-air refueling, and air-to-air refueling requires body tank, and we are not now selecting that, so this is an issue. But I cannot just now select it without checking, so I have to go to body tanks actually. And body tanks, I can see it's an OR for the tank installation. So OR tells me that, okay, I can take actually for a particular configuration, both options, body tank and wing tank together. For sure, I have to go back to the requirements and analyze it, or talk with the tanks experts if for that. But at the end, finally, I know now, and I know we have to select it because that's why it requires is there, and that's why I now create actually the one who's missing. I create now the new selection, and with that we are actually I'm done with my analysis for that, and I make my commit to the server after identifying a missing configuration. Okay, selected body tanks for config 4, and we expect now again, I give back to Marco very quickly that we see that even this selection of the configuration is as well will pop up by Marco.
So okay. We have now, I think we can go now to the presentation back.
Back to me?
No, just last point quickly. So he's updating me that the model has been changed and on the server. So of course the information Mohammed added are now implemented out in the spreadsheet. Now let's quickly look at the few use cases where this approach can be used. So first, I would say when you have to collect variability information from different stakeholders that don't have any understanding and knowledge of modeling methods and tools, it will be more efficient because you don't have to train them on MBSE and so on. The second use case is if you want to be closer to the system expert, because they already use spreadsheets and Excel. I saw many times the use of that, and they are really reluctant and they have resistance using modeling tools. That's why if we bring the spreadsheets, we also increase the acceptance of the solution, variability management solution. And the third aspect shows us that the spreadsheet alone is not enough. So it needs to be combined with a model-based tool, because the task requires also analysis of system and subsystem variability, as we see the interdependencies, the configuration, and their validation. These are just some of the use cases that can be identified to the application of variability management with MapleMBSE. Thanks, Paul. I'm now giving back to you.
Okay, thank you. Okay, so let's just wrap up. Really, just to summarize the what you've seen here. In fact, and thank you very much, guys. That was a really interesting use case of the tool, and you can see some real advantages for doing that. Just to summarize, MapleMBSE is we're providing a easy to use Excel front end for many different tasks in this particular case for variability management throughout the design cycle. Our goal with the tool is to really democratize any of these tasks, including variability management, and to engage a broader range of stakeholders in the process, in the systems engineering process, without having to learn tools like Cameo and or Rhapsody for doing that. And we've seen from today, and certainly we have other case studies that have shown that the use of an Excel-based front end for doing a lot of this kind of work has proven to accelerate the variability definition process by simplifying the information entry and reducing the risk of errors.